So today we're going to talk about partitions of sets. And so let's look at the definition first. So, what is a partition? Well, it's clear. So, a partition of a set, say you have the set of five. And so this set contains only the integer five. So this would be an example partition of a set containing five. And so you're basically partitioning uh, this integer inside the set into sets containing parts that only has that. But the distinction from this with compositions is that this is unordered. So another one is uh, say like 3, comma 2. And so this is two possible partitions of 5. And um, how you would write this is using the partition notation and using part lambda parti uh, is like this number 5. So we can call that n. And so you would call the partition lambda of n. And after this, we can also use notation to use like the length of this lambda would be equal to however many um, lambdas there are. So it's basically just seeing how many possible k's there if you have lambda k. And so we can also write this in a different way using weakly decreasing integers using the tuple form. Tuples are unordered naturally if you do coding. Um, Tuples are lists, but it's unordered and it's like not movable or editable. And so, and like, so they're fixed, right? In this case, if you have a partition of 5, you can just write these as like 5 or like 3, comma 2. And this makes it more easy, also on the person who's writing it. So this is pretty common notation. And so this has 2 elements, that's 1 element. And so, um, we're gonna look at how many partitions are possible for like 5 and these numbers and test it out. But, yeah, that's basically it for now for this section. And so now we want to look at compositions, right? So what is the difference between compositions and partitions? So when you partition a set, you could have this, but then composition will also allow for the reverse, 2 comma 3. But because we did it using like weakly decreasing integers, which means you always have the same integer or it's decreasing. So we can write it as this for the general form. Lambda 1 is greater or equal to lambda 2 is greater or equal to lambda 3 is greater or equal to dot 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 lambda of k. So this would be using the weakly decreasing integers to make sure it is ordered. Because if you have like 2 numbers right here, it's interchangeable, which means it's unordered. They're both counted as the same set. Um, and so, uh, yeah, so that's the difference between the compositions um, and having like partitions. And so, for example, let's first count how many like partitions and compositions are possible for each integer. And so for 1, they're both at 1, right? But then for 2, the compositions would be instead 1, 1, and 2, 1, and 1, 2. But partitions only allow for 2, so you would only have 1, 1, and 1, 2. Sorry, 2, because you do weekly degrees. And so that's the difference. And so basically for any of these, it will be multiplied by 2. But for these, you would keep it as 1. But that also gets more divided if you have like 3 or like let's say like 5, and then you can have like 1, 2, and then 1, 2, 2, 2, 1, 2, and 2, 2, 1. as the compositions for a size 3 uh, composition. And for partitions, you would only have one. It'll be a 2, 2, 1, right? And so for 5, you basically would squeeze these three into one, and then this one, those two into one. So we'll discuss this properly later to help us like write a general formula for a number of partitions for a set. Um, and basically I just want to make sure that like we establish this unordered property. So that's a big difference maker. And it's going to make the number of compositions, um, like compositions, much harder to calculate because compositions you can just do like um, 2 to the power of something. Uh, and then you'll be able to find the total number of compositions that's like using like binomial properties. Like we talked about before, it's like 2 to the power of 3. We'll take all the possible ways to like put this in this order. And so um, actually this is 2 1, sorry. This would be for 3, but you get the point. Uh, like for 3, you would have 3 1 1 1 2 1 2 and you would have like wow, sorry, I meant 2 1 1 2. So this is 4. There's 2 competitions for this one. There's 2 partitions, and then for this one it's just 3 1 1 1 and 1 2. So there's 3 partitions. And so I'm saying for the compositions you can just do like 2 to the power n minus 1. In this case, just 2 to the power of 3 minus 1 is equal to 4, right? So it calculates that easily, but this is harder to calculate. And we'll discuss the formula later. But I just want to go over the notation for the number of partitions. And so if you have partition of an integer, say n, that would be literally representing uh like the lambda thing, you partition that to an integer. And so that's that. And then you can also have like n2 parts, so n into k parts. So you would have like say, well, we can just represent this as like accounting the number of yeah, you can just like do some sum that like sum up the number uh like for each, yeah, you can do like cardinality or like the length of each partition, which should be 1. Um and so that sums up sorry, I mean like you can do this full partition to like see how many of P and K there are for a sum from K of 1 to N, right? Because that's literally summing all the possible number of parts that you can put N into from the partition. For this one, it's just calculating all the possible partitions into K parts. And we'll also go through a formula for that. Because that's harder to find than that. But we can literally do like a recursion kind of with P of N is equal to sum of, as I said, 1 to N. And this is true for all income K. Um, well, of all for all in. And so, for example, we can have like P of 3 into 1. And so if you want to partition 3 into one part, then you would have set 3, just one set. So that would be equal to 1, right? And so we can also have Q, which takes the distinct parts. And so if you want to have distinct parts, then they're asking for like say n. Okay, so this would be equivalent to like if you wanted 3 into 2 parts, you would just want to have a distinct, literally, um, you want to have 2 distinct parts. In this case, all the possible cases is just um, like you have like 2 comma 1, and that's the only distinctness. But if you have like Q of, oh, I'm sorry, it's actually K comma N, but it's the same thing. Um, you want to do into K parts, but distinct K parts, and then of the partition of n. And so if you have like q of 10, and then so q, you want to put it into like three parts, or actually four parts of 10. Um, the number of ways, it's basically calculating the number of ways you can do this. And so like if you think of like 333, count one, you cannot do that because these are not distinct. So they just want like distinct parts. So if you want, what work is like this, right? And so this would have all distinct parts. And so that would be for Q. And so let's find some partitions for the first few integers. So we already counted that for well, for zero is just one because of the principal nothingness. And so you do have one. It's one way to partition nothing um, is itself. And then the number of ways to partition one is one because you just have one. And then for two, you have, well, I think we did it. It was three. That was one, two. Yeah, those two. So you have two. And then, because that's just a one and two. And then partition of three, you would have, I think we calculated it was three because you can do three, one, 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 and two. And then for partition four, you can do four, you can do two, two, you can do three, one. Uh, and then you can also do one, two, three, four. And do three parts, you can do two, one, one. Right? I think that's about it. So one, two, three, four, five. P of four is equal to five. And then let's do the last one, P of five. If you want free time, you can do this for fun. In future videos, we're gonna represent ways, choose ways to represent these each partition, each lambda partition, in a through like a diagram called the Ferris diagram, and also properties that help us use that to get the like special properties like reflecting over a diagonal. It's gonna be pretty fun. Uh, so right now you have P of five. And P of five, you can have five for one. So let's see how many ways to two parts, just these. And also we're talking about partitions into uh positive integers, so you can't we don't do zero here. Um, and so three parts you can have three, one, one, you can have uh two, two, one. You can also have four parts, you can have like two, one, one. And then I think that's it for that. Two, three, four, five. So yeah, I think that should be it. So one, two, three, four, five, six, seven. So you have seven. So the first few numbers might look like um Fibonacci sequence, but it doesn't because it excludes well it's gonna like be kind of more less than this because it's gonna like be less than the growth rate of Fibonacci numbers, which adds the numbers. Um, so I mean, not literally. I don't know, but I can probably guess that it is, but it's not the same. And I'm gonna find a formula. There's gonna be a recursion formula and also an explicit formula that will help us find it. And also, you can't just divide out the number of uh like orders in like one way to one arrangement of this tuple because it's not the same as uh like choosing numbers because or like choosing sets into different other sets because for each order it's not the same because like before I told you there's ones with like um okay with like just like one number or like the same numbers, so for those cases you can't just divide it because there's only one way to do it, so it stays the same, so it makes it hard for you, and you would have to like split up each case to like find the number of partitions by itself. Like for this one, you could do that, divide by two, which is the number of ways to arrange it. But for this, you don't divide by it. So for these, you would have to do something different, which is divide by one. Um, so dividing by the number of ways to do it. To arrange each number would be not correct. And also they're different numbered sets, so like different lengths. And so you can't do that. And then you also can't use multinomial coefficients, which is just like if you want to choose n of like n1 and 2, blah blah blah, you just do this. Um, uh, yeah. Yeah. And so this wouldn't work because of what I just said, or like even the choose formula. And so yeah, we'll talk about partitions more in a different video. Hope you enjoyed. Is I really enjoyed this topic, so I encourage you to discover this further on your own free time.